Hello, this is going to be your 4.6 lecture. 4.6 is all about applied optimization problems. We're going to use the extreme value theorem from a couple of lessons back, and we're going to solve some application problems. Let's start with this one. Suppose we want to design a can that holds 1 liter. It's just going to be shaped like a right circular cylinder. All right, so we want to create the can using the least amount of material possible. So the amount of material is going to correspond to the surface area of the can. The surface area of the can is 2 pi r squared, if the can has radius r, plus 2 pi r h for the outside wall. So the area, I'm just going to call it A, as a function of the radius of the can. So what we want to do, we'll get this all in terms of radius, is a function that we're going to minimize. We're almost there. 2 pi r squared plus 2 pi r. And then we've just got to write h in terms of r. So how can we do that? Well, we know that the volume needs to be 1 liter, and the volume of a cylinder is pi r squared h. So that's equal to 1 liter, which is equal to pi r squared h is equal to 1,000 cubic centimeters. So h, as a function of r, is going to be equal to 1,000 divided by pi r squared. So we can take and plug that back into here. We had a 2-variable equation that we wanted to maximize, or actually minimize in this case. And now we have a 1-variable equation. Our only variable is r. We can clean that up a little bit. A of r equals 2 pi r squared plus 2,000 pi over r. Nope, I didn't cancel my pi's, did I? I canceled one of them, not the other. Just 2,000 over r. So if we want to optimize this using the extreme value theorem, remember we need to find the critical points and the endpoints. So to find the critical points, we're going to take the derivative. Notice r equals 0 could be considered a critical point, but it's not in the domain of our function, so we're not going to worry about that one at all. So a prime of r is 4 pi r minus 2,000 over r squared. We're going to set that equal to 0. We could also see where it's undefined, but it's only undefined, like I said a moment ago, when r equals 0. And that's not in the domain of our function, so we're not going to worry about that for a critical point. So in order to solve this, we're going to need to get a common denominator. So this will be 4 pi r cubed minus 2,000 over r squared equals 0. The r squared can't be 0, so this is just 4 pi r cubed equals 2,000, which gives us, just a little bit of algebra later, r equals the cube root of 500 over pi, which is about equal to 5.42. So then we need to think, so that's our critical point. Critical point here is about 5.42 centimeters. And our endpoints, well, the endpoints were things like the radius is 0 and the radius is everything. So we could, well, that doesn't really work. So that's our real endpoint here, right? We could get a disk of infinite radius and 0 height, and it might, if we did it in just the right proportion, kind of using the same idea from last time, have a volume of 1 liter. But we're not going to worry about that because that is not going to use the least amount of material at an infinite radius. Which means that 5.42 is our solution. Now, in order to triple check that, we could find a double prime. So a double prime is 4 pi minus 2,000, sorry, plus 2,000 over r cubed. Oh, I missed a 2. 4,000 over r cubed. But this is going to be greater than 0 for any r greater than 0. So our function a, pardon me, a is concave up like a cup, which means that our local minimum here, or sorry, that r will be a local minimum, but not just a local minimum because it's everywhere concave cup, concave up, and so it's going to be an absolute minimum as well. We've got a number of other applications here that we're going to use. Give me just a second. All right, so let's take a look. Ooh, that is really fuzzy. Hang on. Come on. Sorry, the video is going in and out. I got it just a second ago. I paused the recording so I could give it something to focus on. I'm gonna try something else. Ooh, that got worse. All right, let me try getting that previous page back on here, see if we can get it to stay with it here. It's not perfect, it's not too bad. I'm gonna go ahead and keep some of that on the screen so that it tries to focus on something. Sorry about that. So if we want to look at something from economics, we can look at revenue. So this is revenue from selling X units. We can look at the cost to produce X units. And then in a very simplistic model, the profit that we have from a business is the revenue minus the cost. So in this case, if we were in business, we'd want to maximize our profit. And in order to maximize our profit, we would find P prime of X. The P prime of X is going to be R prime of X minus C prime of X. So if we're going to try to find a critical point, we're going to look for where this is 0. And so we get the result that if P is the maximum profit, then r prime of x equals c prime of x. So in other words, you maximize your profit where your change in revenue is equal to your change in cost. These, and even p prime, are called marginal. So marginal revenue, cost, profit. So the marginal revenue is the cost, or sorry, is the amount you make to sell one more at any given point. The marginal cost is the amount it costs you to make one more. And the marginal profit is, of course, the difference in those two things. And it's the amount of profit you get for selling one more. So what this can look like for us is if we have something like a cost function and a revenue function, then this would be 0, 0. This is called a break-even point. So with that would be a break-even point. And the maximum profit, we're looking for the distances between these two to be equal, not equal, the distance to be the greatest. So you see the distance here is smaller than the distance there, and that's smaller than the distance there. And somewhere in that zone is where it would be the case, but keep in mind this would be, hang on, which one was the cost? This one is the cost and this one is the revenue. So here would be revenue minus cost. Here, you'd be in a worse situation. You'd actually have a minimum profit, right? Because your profit here would be negative. That's called a loss. So here, your profit would be positive, and that would be the maximum. Over here somewhere, you'd be getting into a situation where you had negative profit again. So at each of these points, though, you have a critical point in your associated function, and you see that in this case, C prime, I did those backwards, that one's C prime, there's C prime, and there's R prime. You'll see that, roughly speaking, they're the same there because I, did a decent job of graphing it. And similarly, if we go here and graph the tangent line where you have maximum profit, then that's where the slopes of those tangent lines will be equal. If they aren't, for instance, if you look at this point, then you get a tangent line here that looks like this and a tangent line there that looks like that, which means that if I move this way, I'm guaranteed to get a larger profit. I don't know which one's the maximum, but I can get a larger profit by moving away from that point if they're not parallel. And so that's why the tangent lines in your cost and revenue functions will be parallel at any given time, in any given max or min. So those are a couple of things. Mainly the rest of this section is an application of the extreme value theorem, which I know we did quite a bit. I'm going to have some lab questions that focus on this, and I'll be posting those to Moodle pretty soon. Have a good one.